Oh, okay. Where's Zach?
He's downstairs.
Chit chatting or
No,
smoking?
smoking.
And Gina?
She's sick.
Is she?
Oh, yeah, Gina. This week has been bad for him.
For who?
For the health and everything. I was sick. She's sick now. Zach was sick.
Okay. What did we say we wanted to look at today as a practice question?
Material.
A materials question. Did we have one in mind? Why don't you open up the exams and let's open up version 2 of what was it, 1718 or something? Oh, so I don't forget.
Oh.
Yeah.
By the way, about the whole volunteering database thing, I have exams at 2 o'clock.
I know, that's why I didn't email you. Or did I email you?
You
Whoops.
email me.
Yeah, okay, that's fine. Yeah. I didn't mean to email the engineers.
Okay.
Did I email all of you?
No, it doesn't.
No, I think I got emailed.
Oh, okay. I also accidentally emailed the PMP students. And so I had one PMP student volunteer, and I'm like, no, that's okay. It's only for IFI.
Yeah.
I am giving you a checklist for your essay. Each question is yes or no. Like, for example, have I written 1,500 words? Yes or no. Did I check the spelling? Yes or no. Okay. And also, on the next page, you can see an explanation of the marks. Okay? So, before you submit your essay, I put the link on Moodle. It's open until the agreed time of Friday at midnight. You need to carefully read this and make sure you have a yes for everything. Okay? So, who can I give 2 to so Gina can get 1? Can I give 2 to you, Doris? Yeah. You might see Gina tomorrow, perhaps. Okay, we're just missing Gina, isn't it? Okay. So remember, the deadline, we agreed, is next week, Friday, at 5 to midnight. Okay?
Where's the link?
It's on Moodle, physics page somewhere. You know, it's called like Upload Coursework 1 or something like that. You'll find it. In fact, there might even be a little notification on the page if you look at the side or something like that. Because usually these things get marked in the calendar if you look at the calendar on Moodle. Yeah. Okay, can you open up the exams and tell me which one we want to do today? Which question to practice? Yeah.
7 years ago.
We're still going strong since then.
Also in Y2K when the world was.
That's true, yeah. Now, you shouldn't reference events that were before some of the birth of the students here now.
I was born.
Yeah, but Harry wasn't.
Yeah, Harry was.
Who? 2001.
Harry's born after 2000.
Yeah.
Yeah, so he has no idea what you're talking about.
He doesn't remember those old days. The 90s.
We remember them.
Yeah.
See, the thing is, South Africa is so behind. I still grew
You
up
got to say
with
you
that.
had Y2K in 2010, is it?
Well, no, like all the internet and
Yeah,
sort
okay.
of the
Yeah.
adoption of that and TV and
Yeah,
stuff. It was all
you
a
just
bit delayed.
recently moved from dial-up,
Yeah.
was it? Okay, so what exam are we going to have a look at today now? I think we want to be doing a material section B question.
Yeah, let's do that Young's modulus one. And, I think it's B2. 60.
That Young's modulus materials question. Yeah, just tell me the exam and the question. Yeah. 1718? 1718 version 3? B1.
Kind of.
Kind of Young modulus. How's a kind of Young's modulus?
Half of it,
Oh yeah, that's fine. I don't ever think you could get a full question on Young's modulus. There's not enough in it, you know. Right, do you have this open?
Question B1.
Yeah.
Yeah, B1 1718 version 3.
Yeah, got it.
You got it? Yeah. Do you have it open, Harry? This one? Right. Stopwatch. Wait, don't start yet. I haven't got the stopwatch going.
No,
1718 B3.
Okay, you got it open? Right. Let's see how you can do with this one. 20 minutes. There's only 1 second in, Dorian, and you're already sighing. Oh, you're a bit sick, huh? Okay. Sketch a graph of stress against strain.
No, we'll see the result. Or perhaps why.
Strain.
That's what the hell I know. I didn't got it from somewhere else.
Stress. Now, stress is force over area. So the unit is Pascal, isn't it?
Do we have to write it?
Oh, I don't know. I'd have to check the marking scheme, but I would always play it safe.
Oh, stress and strain have no units.
No, they. Zach.
I don't think we do.
Stress has. Strain doesn't. Right? Yeah, to the breaking point. So it's linear, then it breaks, and then I think if I remember, which I don't actually, I think it levels off.
Yeah.
Yeah.
Yeah, and it continues because the next part is on the graph.
So on the mark scheme,
Yeah,
it's like really steep, levels off, and then goes down.
You see, mate?
Yeah, go down to.
You see?
I'm not sure where the maximum
Oh, they have the
is.
minorities.
I wouldn't be so concerned about that.
What do they want to?
They drew it.
Yeah, they
Yeah, they
want
drew
the
it.
elastic
And then,
limit,
yeah.
the plastic region, and the tensile strength. Maximum tensile strength.
Oh yeah, we'll get to that in a moment. So if I need to change my graph to make sure these are included clearly, I will. So the position of the elastic limit. So this here is the elastic limit. Okay. The position of the maximum tensile strength. Now the maximum tensile strength is the point at which the brass wire snaps.
That's why I thought it would be the end of the graph.
It's not?
Well, we just think about this for a moment. So, stress. Let me just go to the side for a moment. Young's modulus is stress over strain. Okay, which is force over area over extension over length. Yeah? Now, these are constants. They never change in the experiment. Well, actually, that's not true. Sorry. So let me just.
Extension changes.
Yeah.
So, when you say that if you stretch something, the area becomes smaller?
Yeah, but we don't really consider that effect on it, you know. So Young's. Okay, so what am I trying to get to here? Sorry, I'm getting myself confused. Which is on the y-axis? Stress.
Can I tell you a label there, Max?
No. Don't.
You looked at them. What did they put? Okay, sorry.
I like your Star Wars reference, by the way. So
Huh?
Return of
database.
Yeah. Oh, flip.
See, I thought, wouldn't it be where the gradient is?
Thinking. Stress equals, sorry, I keep forgetting what's on the y-axis. Stress, fine. Stress equals Young's modulus times strain. Yeah, what the heck happens when it breaks? I'm trying to think what happens.
See, initially I thought it would be where the graph stops. Because it doesn't go on forever.
That's what I'm inclined to think too.
It's not all basic.
Interesting. Oh, rats. Where do I put the tensile limit? Ah. Is it here?
Yeah, but there's something goes after it.
Continues down?
Yeah,
Okay, but they call this the tensile.
yeah, just the point where it stops before it starts declining. So where the gradient is zero or becomes negative.
Yeah. So look, I was thinking deeply about this, perhaps too deeply. I was trying to figure out what happens when the wire breaks. You know, I was thinking things like, well, the extension would become infinite.
Yeah.
You know, I was thinking that. But what about the force? Well, the force could be infinite because it's not connected. I was getting very confused. And then I realized, no, the simplest thing to think about it is, remember the slope is Young's modulus.
Yeah.
It doesn't make sense for the Young's modulus to be negative. So as soon as Young's modulus goes negative, this must mean there was a breakdown in the values, and so it broke. So I'm going to say this is the tensile strength, and this is at the point where the gradient it becomes a negative. It doesn't make sense anymore.
Yeah, but that's what I'm saying. Why wouldn't the graph just stop?
I would think it's not meaningful to continue the graph after that point, you know. So that's, you notice, that's why I
Yeah.
dot it. Now, Zach, it's very possible that whoever made the graph just couldn't have been bothered to dot out the line,
Yeah.
you know. Right, and the next one, the region of plastic behavior. Right, so here is elastic, and here is plastic. Okay. Continue?
Yeah.
So, I have 7 marks. In an experiment to determine Young's modulus, blah, 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 here's the data. So, what have we got here?
Copy pasta.
So, we got a load, and this is the reading.
Yeah. So extension is 0 for the first one.
Yeah.
And you just minus all the linear.
All of these have to be
minus.
reduced by 1.07, isn't it?
Yeah.
Yeah. Okay. I wonder if I can.
Don't need to read them out for you, sir.
Well, I'm just
Or you're
wondering.
gonna copy pasta again.
I'm going to see
You're
what
gonna
happens.
figure out how this print screen works.
Yeah, let's see what happens. Not today.
Oh, why don't you open? Oh, there we go. I'm like opening the window you were in
Yeah.
with the print screen right there, and then selecting that.
Oh, it doesn't matter. Screw it. Okay. Right. Just
that one. Click.
No, it doesn't matter. So give me the values, please, here. Because what's happening, is, to be clear, is you have the length of the wire, and when there's 0 kilograms, that means there should be 0 load, which means there should be 0 extension. So the original length needs to be subtracted. This should remind you of something you did recently. Yeah, well, do you remember when you did the experiment yesterday? You know, in the absorb what's it called? What's the experiment? Bradford's. Remember, we had to subtract from all the A values. Yeah? Kind of doing something similar here, right? You could call these the uncorrected extensions, and this would be the corrected extension. So, yes, give me those values here.
0.99.
Hang on, okay, 0, 0.99.
2.05.
Okay.
2.97.
Okay.
3.98.
Yeah.
4.96.
Yeah.
5.95.
Okay, so that's fine, right? 2 marks. And then make a graph. Yeah.
I was a little confused. So the weight is, I was thinking, is it possible to add it the way before? I mean, so for example, like it's not 3.12 minus 1.07 is minus 2.06.
Oh, no, the extension is always from the original length, not the previous length. Oh, I see what you're thinking. Yeah, no, it's always at the original compared to the original 0. Yeah. Okay.
What does that vernier really do?
Vernier is the name of the instrument used to measure it, I believe, because it's good at measuring small. These are all millimeters, you know. It's good at measuring small distances because look at the accuracy here. You have 2 decimal places of a millimeter. You know. Okay. The graph for 5 marks is nice, where you plot the extension against the load.
Not the load against extension like I did.
Yes. And look, Zach even told you which is which. So, the extension in millimeters. Now, I'm kind of bummed out here because, yeah, the load is in kilograms, but, oh, do I convert it to newtons? Or do I leave it in kilograms?
Give it in kilograms.
I kind of want to do it in newtons. But,
But they say load, so.
The one is kilograms.
yeah, well, to be perfectly honest, I think I'd give the marks in both cases. Because usually it should really be newtons. Should really be newtons. But we can do it in kilograms, it's fine. Okay? I'm not going to do this accurately. You know the deal. You plot them, and did you get a straight line? I would hope so. Right? What's the gradient? Okay, so the gradient would be, let me see, I could probably get it here. 5.95, is it? Over 3? Is that right?
Yeah. It's 1.99, 1.98, 1.97.
Oh, but is it 1.9?
Yeah, depending on which points you use.
Okay, fine. Yeah, something like this. Oh, we're at the end of it already. Additional measurements on the wire were given. Its original length as... Oh! So, Zach, you were asking me, should we consider the weight?
Yeah.
This 1.07 that we're correcting for is an extension caused by the weight of the wire.
You see?
Yeah.
So wouldn't you leave the extension as 1.0? No. They write the 0 as the...
Yeah, well, you see, what you're doing is you're calibrating so that you neglect the...
Oh, the weight.
Yeah, so we're correcting the values here. Yeah. But yes, so the original length was 2.43. It extended by 1.07 millimeters because of its own weight. When you hang it from the ceiling, we zero that by subtracting 1.07 because we're only looking for the extension past the natural length, which can include a stretching effect from its own weight. So, anyways, original length was 2.43 and the diameter is that. Use these values and the gradient to calculate Young's modulus. Now, we'll have to think about what this slope represents. So, this slope is the extension over not quite the force, is it?
Or not yet.
Yeah. So you can say 1.99 is equal to extension over mass. Now what I could do, if I divide both sides by g, I get mass times g, which is now force, like that. Okay. What I'll do now is I'll flip both sides. So I'll get force over extension. Okay. If I divide this by the area and divide this by the area, you see what's morphing into?
Yeah.
And then I'll divide this by the natural length. So that's like multiplying, I'd have to multiply this side by natural length.
Yeah.
But now I've morphed this into stress over strain, which is Young's modulus. So Young's modulus will be the natural length, which is 2.43, times 9.81 over pi times radius squared times 1.99. And the radius is 0.274
Times 10 to the minus.
yeah, over 2. Now wait. I need you to tell me what you think, okay, because it matters. The original length is 2.43. That is nearly the same as the natural length, okay? If the wire was lying on the ground, then its original length and its natural length, i.e. the equilibrium length, will be the same thing. However, if I turn it on its side, when they say the original length, do they mean with or without that little tiny extension, you know? The one. Now, it might not matter in the final calculation because 2.43 versus 2.43 107. Will that make much of a difference? Probably not. So it's a moot point. Anyways, once you get the answer, we can see if we stick in the 107 if it'll make any difference. I doubt it. Okay, sorry, now continue. They times by 4?
Yeah.
Oh, do you know what they probably did, Zach? They probably took that 2 squared to the top.
Oh, that's what I left out.
It should be big. 2 point.
0.03 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's close.
So, no, not 11.
1, 2, 3, 4, 5, 6, 7, 8.
Where did
Which is it? 8 or 11 or
8.
something?
8.
8, okay.
No, they said in the marks.
probably the difference is probably 0.001 times 10 to the power.
So,
So
if you were to round it to 3 significant figures, it'd be the same. So it's good enough. Yeah. But is that matching the marking scheme?
No. Where is this 10 to the 11?
Ah,
What?
They screwed something up, huh? I didn't screw anything
So
up.
their formula is 4 times 9.81 times 2.
Wait, let me write down their formula. Well, there's one easy way to check this, right? What's the material? Was it brass?
Yeah.
Okay. Harry, could you Google Young's modulus for brass? Now, Zach, you read out the formula. Let's see what they wrote. Is it? Oh, did I give you brass?
Yeah.
Well, let's just Harry double check on Google. What's the formula?
4 times 9.81 times 2.
Hang on, 4 times 9.81.
Times 2.43.
Oh, hang on now, and I need to compare this to what I wrote. So, I'll tick it off. They said 4, which is
Yes,
probably the
which
2.
is that,
Fine. They said 9 times 9.81.
Yeah, times 2.43.
Okay, good.
Over
Yeah.
pi
Yeah.
times 0.274
Yeah.
times 10 to the minus 3
Yeah.
times
Yeah.
1 over 1.987 times 10
Ah.
to the minus 3.
Oh, Stephen, what did... No, that looks right. Do they have a square?
No. Yes, they do have a square.
They do have a square.
Why is the gradient times 10 to the minus 3? And why is it 1 over the gradient?
No, well, that 1.99. Oh.
No, 1.987 times 10 to the minus 3.
This is because the grade
Wait,
is in milli-
That's it. Guys, look up.
Oh, yeah.
Look up, look up, look up, look up. That's okay, Harry. I found it. It's my mistake. My mistake was this here.
Is it
I forgot that it's in millimeters. So really, what you would now look up. If you multiply both sides by 10 to the 3, then x times 10 to the 3 will be in meters. Okay, so the m should be times 10 to the 3.
It's 1 over.
What was my m? 1.99.
Why is it 1 over?
Oh,
When you swap them, it's 1 over g over 1.99.
yeah. Did we not type this in on the calculator?
Because that would mean it's on the top then, right? That doesn't make sense.
Times 1 bracket 1 over 9.87.
I'm confused.
Let me type it in my calculator.
I'm confused.
Where did you go on the place? In here?
Stephen, do we have to use the gradient?
No, we don't, but I'd like to know my mistake. Let me just think.
If you put 1 over, it doesn't work. It's like 8 point something. But if you do it without, it's right. So the mark scheme has to be over there.
Is it 2.03?
Yeah.
Yeah.
Okay, now hang on. If I just think for a few seconds, I can fix my answer. It'll be right. Okay? Just give me a moment. My problem was I forgot that it's in millimeters.
Yes.
Okay? So the problem is that 1.99.
Should be.
No, just please. I can do this. I just need silence. My problem is I was a bad teacher and I never wrote my units here. So when I said m is 1.99, I should have said 1.99 millimeters per kilogram. Whereas I'd much rather have meters per kilogram. How much is a milli? 10 to the minus 3. So this 1.99 is 0.00199. Okay? So, if I just replace that with 0.00199, my answer will be 1,000 times bigger, which will make this 2.03 times 10 to the 11 pascals.
Yeah, correct.
I know. I told you I could get it. I just needed a minute to think. Right. Now, Dorian, you said there's another way to do it. On reflecting on how I did it there, I would hope that there is, and probably a nicer way to do it.
But I also did it wrong because I forgot the extension was giving me this.
That's okay. That's okay. You're in good company because I did that too. Right.
So why is one over?
Yeah, it doesn't explain.
I don't know what way they did it, and I don't want to know. I just know that I got the right answer now, and I'm happy with that.